Hello, everyone. Welcome to week 2 of our course. And for this week, we are going to tackle about electric field and electric potential. Okay, so let me share with you my screen. And I will be posting the slides in your canvas again for this week. So, okay. So for last week, we already discussed about electrostatics as well as electric force in the Coulomb's law. So this time, since we already discussed that if an object will be charged, it could be either positive or negative. Okay, so with that, there will be electric force that a charged object will exert to another charged object, etc. So they can either repel or attract with each other. Now, what what happens when there is an electric force? Okay, so surrounding the object will be the electric field. Okay, so we have our analogy for that for the electrical charge and for the mass. Okay, so the electric field is the space around an electrical charge, and it is just like the gravitational field that is in space around a mass. Okay, so say for example, this is our positively charged object, and since it is positively charged, it can attract or either repel with another charged object. So the region of space here is what we call as the electric field. We cannot see the electric force, or we cannot, but we can definitely feel the electric force. So this is a type of long range force. In the same way, the gravitational force is also a long range force. We cannot see it, but we can feel. Okay, everything is being pulled towards the earth's core. Okay, so an electric field is the space around a charged object. Okay, so this electric field is being represented by the electric field lines. As what we had talked last meeting, that we have an object can be positively charged, an object can be negatively charged, and we can determine the charge due to we can determine by using our triboelectric series. Okay, so if you rub a pen and your hair, okay, one will be positively charged and the other will be negatively charged. Okay, so here the electric field is represented by the electric field lines. So there are rules on how to draw electric field lines. Okay, so later we will understand or we will talk about those rules. So we can if you are familiar with this, the Van de Graaff generator, this builds up static electric charges. So when you put your hand in there, your hair will go up. Okay, so you are very familiar with that in physics or in the videos or in photos. That is the Van de Graaff generator. Okay, so how are we going to compute the electric field vector E? We are just going to divide the force by the positive test charge. So just simply divide electric force over charge. That will be Newton per coulomb. Okay, so I have here an example. As what I've said, you just simply divide the electric force by the charge, and I give you the answer here. So that will be for your practice. Okay, so let's now proceed to electric field lines. For electric field lines, okay, so say for example, we have two positive charges. We have the net electric field in any point of our electric field. Okay, so electric field lines are lines that indicate the strength and direction of the electric field. The more dense the lines, the stronger the field. The electric field vectors are tangent to the curve. We have here a simulation wherein you can do your virtual lab. Okay, you can go to this website for your virtual lab, and our module for laboratory, module number 2 for laboratory, is also there on your lab course card. Okay, so we can determine the field which is stronger by the number of lines. The more denser the lines, the stronger the field. So between A and B has a greater amount of number of lines, so that means that it has a stronger magnitude of electric field. Okay, so using our previous formula, electric field is equal to the electric force per unit charge, and Coulomb's law, we can derive the electric field is equal to K Q over R squared. Okay, and this is also derived in your module. Now we have another example. The answer is there given for you, so you can work on this by yourself. Okay, now field lines for a point charge. Okay, so here there is 10 nanocoulomb of charge, while the other one is 1 nanocoulomb of charge. So the magnitude is greater, therefore it must have more field lines. Okay, so what will be our rules for this? The field lines begin at positive charges. Okay, so our field line here, we go from positive going to the negative. Okay, and the field lines begin at positive charges and end at negative charges or infinity. So positive always away and negative always going towards. Okay, so as what you may see here, you have the arrows from positive going away and then the arrows towards the negative charge. The number of lines drawn leaving a positive charge is proportional to the magnitude of the charge. So the greater the magnitude of the charge, the more field lines there will be, and no two field lines can cross each other. There should not be overlapping of field lines. So this is an image of field lines under a microscope. Okay, so there are electric field patterns. So as what you can see here, these are both positively charged objects. So the field lines are going away from it. Now here, these are both negatively charged objects, so the field lines are going towards it. Okay? On the left side, the greater the magnitude of the charge, and on the left side, the lesser the magnitude of the charge. Okay, now, as you may take note, these are like charges. These are like charges, so they are repelling each other. Okay. On the other hand, we have our positive and negative. They have opposite charges, so they are attracting each other. Okay. And again, the positive is going towards to the negative. And the right side has greater magnitude than the left side. Okay. And on the other hand, we have a positively charged object and a negatively charged object. For the positive going away, negative going towards it, they are attracting each other. And the positive charge has a greater magnitude than the negative charge. Okay, so I have here exercises for you guys to answer by yourself, to practice answering. Okay, so practice this at home. Okay. By the way, before we proceed to electric potential, I will also be giving you for a while. I will also be giving you another other examples rather for field lines. Okay, hold on for a minute. All right. So here it is. I will be sharing my screen again. Okay, there we go. Okay, so here, let's just have number four. Let's answer number four. We are just answering those that are confusing. Okay, so You are given this diagram. Several locations are labeled A, B, C, D, and E. Now you are asked to rank these locations in order of the electric field strength from smallest to largest. So how are we going to determine which of the following would be smallest or having the smallest value to the largest value? Okay. Now we can determine that, okay, the electric field strength we can determine by the number of lines, as we had said. Okay, now let's take a look at the point D. Point D is somewhat in the empty space. So there are no field lines there. Okay, so that means that letter D, or no, not letter D, point D has the smallest field strength, electric field strength. Okay, why? Because no field lines are there. I'm sorry for my penmanship. That is letter D and that is less than. Okay, now next to letter D, which point has the lesser field line? Would it be A or E? Okay, so this time it would be point A. Why will it be point A? Okay, point A is only there at one field line. Okay, so with regards to that one, when we are going to compare it with point E is in between two field lines. So it is stronger than point A. Okay, now next would be what are left are points B and C. For points B and C, we can determine the strength of this, okay, again, where the field lines are more concentrated. Okay, so here for point C, there are only two field lines that are really close to each other. Okay. Well, for point B, there are more field lines that are closer to it. Okay. So that means that C has the lesser electric field strength and B is our point having the strongest field strength. Okay. Again, D is our weakest because it is in the empty space, no field lines are there, followed by A, which is only there at one field line, followed by E, there are already two field lines, point E, for point E. Now followed by point C, the field lines are closer to each other, and for point B, the field lines are more concentrated. Okay, so that's how you're going to determine the electric field strength. Okay, so this is very easy. Let's have this again, the ranking. Okay, so if you are going to rank which is stronger, which is lesser, okay, it can be easily followed that A has greater number of field lines, so B must be lesser or weaker than A. Okay, and if we are going to determine what charge is it, we can determine that by the arrows. Okay, so A here going away, so A must be positively charged, and B is going towards, so B is negatively charged. Okay, and so on. So we have C is weaker than D, D going away, so it is positive, C is going towards, so it is negative. And for this one, G has the least number of field lines, followed by E, and then charge F is the strongest. Okay, now what will be the charges? For G going away, positive. For E going away also, it is positive. And for F going away, it is also positive. Okay, and finally, we have H, I, and J. Okay, the least is J. Sorry, that must be J, followed by H, and then I is our strongest charge. Okay, so J going toward. So what does mean? J is negatively charged. For H going towards, H is negatively charged. And for I going away, I is positively charged. Okay, so that's just it for the field lines. Now we will proceed to electric potential. Okay, so when we say electric potential, of course, we have our electric potential energy. That is the energy that is stored for electric charges. Okay, so our orientation will be always from higher potential to lower potential. As what you can see here, you have our plates. One is positively charged, the other is negatively charged. Here, A has the higher potential going towards the lower potential. So the electric field is always going towards that direction, from higher to lower potential. And our formula for electric potential is just equivalent to the electric potential energy divided by the charge. So we have now our volt, which is equal to joule per coulomb. Volt comes from the scientist Alessandro Volta, who first invented the battery. Okay, so by that time, Alessandro Volta invented a battery as big as a room. Okay, but now batteries are very tiny already. They are in nanoscale. Some batteries are in nanoscale. Okay, so we have our derived formulas also. These are shown in your module. You can take a look at that, and examples for this are also in your module. Okay, so that's it for week 2. That's it for week 2. And if you have questions, you may message me on Canvas. Okay, so you can start working on your module anytime you want. You have the flexibility for that. But I do hope that you will start working on your module before our, when is our schedule again? Before Thursday of each week, okay, for our consultation hour. Okay, again, this is our lecture recording, our TDOA, and we have our consultation hour. It is 10 to 11 a.m. every Thursdays. Okay, so if you don't have any question, if you don't have any concern, you may not come to our consultation hour, but I will be there. I will be online. I will be here in Google Meet, and I am online waiting for you. 10 to 11 a.m. Thursdays. Okay, so if you don't have questions, you may not come. But if you have questions, you have concerns, if you want me to discuss further, I can. All right. So let me remind you again that the deadline for this module, for the submission of module, is on February 27. Okay, so you have more than enough time to work on your modules, of course, to pass this subject and to study, because our exams will be open camera. Thank you very much for coming to class. Okay, so if you have questions, concerns, just message me on Canvas, and um I will answer all your queries there. Okay, so see you next week. Subscribe to this channel and to my other channel, The Other Side of